my people. So here we have, this is where we left off. All right. And now that we've introduced the idea of acceleration, we've really nailed down the idea that velocity can change. Velocities aren't always just average velocities. They can go from one thing to another. So with that in mind, and the idea of acceleration, we now really should do our best to come up with a more complete list of variables and how we can use them. Okay, so new ones old ones that we'll keep for sure. Displacement, delta x, meters, change in position. We'll keep time, t, measured in seconds. Duration of whatever you want. Travel, how about that? Duration of travel. What else? What else? Well, I'm going to add something new here. Initial velocity, v naught, measured in meters per second. Well, let's see. Velocity at the beginning. As opposed to final velocity. V, measured in meters per second. Velocity at the end. If I'm going too fast, just hit pause. Acceleration. K, measured in meters per second, or more typically, meters per second squared. Rate of change of velocity. What else? I suppose it's not the worst thing in the world to keep average velocity here. V bar, meters per second. Definition, yeah, average velocity. Right? Average of velocities. It's the definition of average velocity. Average of velocity. Velocities. Now, what do we do with these? As we move forward, we're going to talk a lot about changes in quantities. All right. What do we use symbolically, mathematically to mean change? We use delta. Delta means change. All right. And to find the change in anything, right? Like for example, delta V. Well, we always do the final value minus the initial value. You'll see that in a minute. And some stuff we know already. Well, we know, let's see, V average is delta x over t. We know that acceleration is delta v over t. One more thing we know that V average, oh wait, we already have that one. Oh yeah, we could also write V average as, well, how about this? V naught plus V over 2. The average of velocities. Okay, we're going to use these three equations to derive three more equations, specifically for things that accelerate. Okay? Now, use kids, use guys, don't have this slide, I don't think, which means you don't need to be able to do this. This is a show, but it's not a magic show. What we're trying to show you is that these equations that will look complicated are not magic. They don't come from nowhere. They don't come from nowhere. That's a double negative, which means they do come from somewhere. Here's where they come from. And what are they? You'll see them in a minute. We'll start with this. A is delta V over t. How do we do delta V? We subtract V initial from V final. Now, let me reiterate. You do not need to write all this down. I will never ask you to derive these equations. I want to show you that equations come from somewhere. They're not magic. Now, one thing we can do with this is just do some algebra to rearrange it and solve it for something else. Let's solve it for final velocity. We multiply both sides by t. Let's add v naught to both sides, and we get the following expression. The final velocity that an object has, well, if you want to know what it is, you can take its initial velocity and then add this factor, how much its velocity has changed per second times the number of seconds that it changed at that rate. That will tell you how fast something ends up. Well, it'll tell you something's velocity at the end of some time interval t. Okay? So that's just some hopefully pretty straightforward algebra. Nothing too crazy. Let's start with this one. Now, if we rearrange and solve for delta x, we get that. Well, what's a way we can write v average? Remember, we take the two velocities that an object has, add them up, divide by 2. Just like for an average of a test score, of 2 test scores, add them up, divide by 2. Well, look at this. We have a different expression for v final. So instead of v final, let's write v naught plus at. So there's a couple of things that happened. I took this 2 here and turned it into a 1/2 times. Here's the v from here, and here's the v naught from there. And here's the t and the t. We can combine those v naughts in there. We can distribute that t through there, and then distribute the 1/2 through there. Now, typically we don't write this, typically we don't write this x naught in there. All right, but typically, so I don't know why I have that one, but this is the way that you'll see this equation written. Right, delta x is, right, 1/2 times 2v naught t is just v naught t. 1/2 times at squared is 1/2 at squared. So sort of forget about that one. Same thing. And third, let's start with that expression, but we have, and if we rearrange to solve for t, do some algebra, right, multiply both sides by t here, divide both sides by a, yeah. Let's see, what did we do? Oh yeah, okay, so just literally take this expression, move it over here, but then take this stuff for t and put it in there. All right, let's pull out the 2a, or move it over to the other side, and we get v plus v naught times v minus v naught is 2a delta x. We FOIL this, and we get v squared minus v naught squared, right? The FOIL part, right? The inside would give us plus v naught. The outside would give us minus v naught. Those things add to 0. And we get this perfect squares thing, isn't that what that's called? Let's solve this one for, is this still recording? Hey, stop it. Hey! Uh-oh. Still recording, are you? Oh, excellent. And let's just rearrange to isolate v final. But we're actually just going to leave it as v final squared. Okay? Those are 3 what we call kinematics equations. And we use each one of them in a different example, or for different examples, for different instances. And we'll get some practice in a minute with when you use each one. Okay? They each are valuable in different places. So really there are 4 equations. And so this one here is really just delta x is v average t. Don't give up on that one. Boy, is it useful and simple. All right? I would try, almost any time you can to use that, as long as you use it carefully. And by use it carefully, I mean you better darn well consider what that actually means. Well, it means all that. But let's look. What does this equation have? Well, it's got a delta x, it's got a v naught, it's got a v final. It doesn't have anything about acceleration, but it does have a t in it. So there will be some problems that you'll see where you're told 3 of these 4, and you're asked to find the 4th, then it's a pretty good idea to use that equation. There'll be some other equations, or some other examples, excuse me, where you're given a V naught and a V and an A and a T, but not anything about delta X. Right? If you're given 3 of these 4 and asked for the 4th, use this equation. There are some examples where they'll discuss a delta X and a V naught and a V final and an A, but nothing about how long anything takes. Good idea to use this equation. There'll be some times where you get the idea. This one has delta X. It has V naught. No, it doesn't have V final. It has A, though, and it has T. So notice, they all have a different thing they're missing. This one has no A. This one has no delta X. This one has no T. This one has no V final. They all happen to have V naught. Coincidence. So the idea of this slide is we should be able to, based on a question, figure out what we're given, what we want to find, and therefore which equation has all those things in it. Let's try one. A particle, generically, is moving with a velocity of 60 meters per second in the positive x direction at time 0. Blah, blah, blah. The velocity decreases uniformly to 0. What was the acceleration? All right. So, first good step. Really 3 steps. Maybe 4. Let's do all these steps. What are we given? Let's identify some quantities we are given and what we want to know. The particle is moving with a velocity of 60 meters per second at time 0. That means that the initial velocity is 60 meters per second. There's a time interval of 15 seconds. Here's a tough one. The velocity decreases uniformly to 0. The final velocity is 0. What was the acceleration? This is a great first step. Write down what you know and what you're looking for. The absolutely necessary next step is to find an equation that has those 4 things in it. Pause and find that equation. Ready to go. Good. You should have found the following equation. Well, all right. So here's where this is kind of annoying. But if we, with the last 4 equations, you would use this one. That actually comes directly from this one, which we knew before. And the nice thing is it's already solved for A. So we're just going to use it in this form. Oops. Sometimes in Regents or other courses we write explicitly V final. So this is V minus V naught over T. Notice, if we use algebra to rearrange this equation, we will get that equation for A. All right? So this is a step you absolutely need to have. Write an equation. This is a step you absolutely need to have. We call this SIFU. Solve equation for unknown. Do the algebra. Substitution is a necessary step. A is 0 minus 60 with units, meters per second, divided by 15 seconds. A equals negative 4.00 meters per second per second. Dunsky, Dunsky, Dunsky. What's the significance of the sign of your answer? You tell me. Okay, folks, onward, onward. You've got something to answer for on Monday when I see you. Jules Verne, 20,000 Leagues Under the Sea. Jules Verne proposed sending men to the moon by firing a blah, blah, blah from a blah, blah, blah with a blah, blah, blah. What would a blah, 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 blah? Let's write down the things we know. the things we want to find. We know that, okay, that must be delta x. A final speed we're looking for what unrealistically large acceleration? Question mark. We need one more thing. Oh, sure. If this person's fired out of a cannon, we have to say that at the instant that the, what do you call them, person starts accelerating, their speed is 0. What's delta x? Let's see, what equation has these 4 things in it? Well, I would say that it's this one. Oh, you should pause to find it, of course. V squared is V naught squared plus 2a delta x. Equation slash CFU. That's V squared minus V naught squared is 2a delta x. That's A is V squared minus V naught squared over 2 delta x. Substitute. A is 10. Uh-oh. I don't like this. Let's use what we know about kilometers. There are 1,000 meters in one of them. I'll write this as 10970 meters per second squared. Now you can just do this if you want, but whoops, that's supposed to be crossing out the V naught squared. Just didn't come far enough over. So we can leave that like that. 2 times 220. Don't forget to square. 10970 squared divided by 440 equals, holy crap, acceleration is 2.7 times 10 to the 5th meters per second squared. Yes, that's unrealistically large to ask you to go through. Eventually we'll figure out that you've heard of like pilots or maybe on roller coasters pulling G's. You ever heard that? Pilots can pull like 6 G's for like a second or two before they pass out. Well, 1 G is about 10 meters per second squared. You'd have to pull 27,000 G's in order to do this. It would destroy you physically, literally. You wouldn't live. Onward! You do it. You do it. You do. Okay, people? Okay, don't forget your quiz on Monday on all things graphing. All things graphing. X versus T, V versus T, translating from one to the other, calculating things based on those graphs, talking qualitatively about motion based on what you see on a graph, maybe even drawing a graph based on some qualitative description of motion. Okay, those are all things you need to be able to do for your quiz. I hope you had a great weekend, or have a great weekend, or both. Bye.